good. So I don't know who that young guy is. I think I need to do a new picture with the little more gray in the beard. So I'm going to talk a little bit about determinism. You've heard me talk about this before, but I wanted to take a little bit of a dive, go a little bit deeper. You know, when I do these keynotes, I always have to worry about, you can definitely get too technical. But at the same time, if we go a little bit under the covers, we can see what's really happening in Wi-Fi 7 and what's really happening in the industry. And so I'm just going to do that. I'm going to scratch the surface a little bit, because people say, well, do you really need determinism? Do you really need predictability? Well, I'll tell you one thing. I talk to a lot of customers, and I hear this all the time. They want more predictability in their networks, especially when you talk to IT departments, people that run networks. Or if you look at this convergence we were talking about just a minute ago, one of the things that you really need when you start thinking about converging 5G and Wi-Fi is, can you do that with a predictable capability? In other words, if 5G is going to offload into some of these Wi-Fi networks, can you get a carrier class experience? I can remember in the early days of Wi-Fi, which by the way is not that long ago, you talk to some of the service providers and they say, well, how many Erlang am I going to get for a busy hour? And on Wi-Fi, and we would say, it depends. And that's not an answer they like. It depends. They want this to be more predictable. So as we converge these networks together, I think these things start to become really important. The other thing that I've noticed in talking to customers, even in the enterprise space, is if you ask them, do you have a mission critical application that you run on your network? And I've yet to have an enterprise tell me, no, we don't run any mission critical applications. In fact, the message is always that something has to be prioritized over something else. And this is one of the things that I really see as a big difference between 5G and Wi-Fi, is that Wi-Fi, or in the enterprise environment, you don't want to be fair. You want to prioritize certain traffic. And so if you're in a hospital, you might prioritize that connection to the heart rate monitor or the medical equipment over what the guests are doing to watch YouTube or some of these other types of activity or web browsing. And so you get these differences in services, and so there's this policy component. And so can you apply the policy to that experience, and can you get a predictable end result? So to do that, there's two things that you have to achieve in wireless, because I talk to a lot of engineers, of course, being in the CTO organization, and how do you do this? Because people will often say, we're in an unlicensed environment. Predictability is off the table. Anybody can come in, anybody can generate interference. So what do you mean predictable? What do you mean deterministic? That's something that can't fundamentally be achieved. But what's interesting is that there's two things that are really happening in the industry to solve this and have to happen. One is you have to have a stack that can do it. And if you look at Wi-Fi, and I'll take you through a little bit of a journey on Wi-Fi and what we've been able to do and what we've done in enhancement-wise, and I'll show you some of these stack changes or capabilities that are allowing us to do scheduling on the network to get this more predictable result. Now, the other thing that you have to make sure that you're doing is accommodating interference, because it is unlicensed. So again, I'm talking about Wi-Fi specifically here, and if it's operating in unlicensed, it doesn't matter how smart you are. All these things we do around radio resource management, all these things we do around scheduling, if you're getting broadsided by interference, then what's going to happen? It's going to up those error rates, you're going to retransmit, and your predictability just went out the window. You no longer can determine the latency of the network. In fact, you can't even determine the throughput. So this is something that's been happening in the enterprise space for a long time. So what do we need? We need scheduling. We need to be able to take a policy, and that policy needs to be to affect that lower layer scheduler, which is what happened really when we went into Wi-Fi 6. And in interference, we need to be able to avoid it, we need to be able to schedule it, and we need to be able to mitigate it. So how are we doing that? So you may have seen me present this before. I'm not going to spend too much time here. I want to actually dig into a little bit of the technology. I said I'd go a little bit under the covers. But here you can see sort of this very high level view of progression that's happened in Wi-Fi. Because if you go to Wi-Fi 5 and earlier, what we were really doing, because it was, and many people would say, hey, this is a best effort network. right? If it's best effort, that kind of throws determinism, that kind of throws predictability out the window, right? And what we did in Wi-Fi, and it became extremely popular, in fact, it carries like 83% of the world's traffic. It's amazing. It's more popular than anyone imagined it would be when it was created. And so what happened is that you'd over-provision these networks and you'd under-subscribe them. Now, if you've run a network, and I know many of you here have, if you got up over 50% channel utilization in Wi-Fi, what happened? It started to degrade. And in fact, if it was a high-density network, you'd start getting these collisions, and then things would back off and retransmit. And if there's a lot, like I said, if the density of the devices, which is more and more common as we add things to these networks, smart buildings, all that stuff you're connecting at home right to your light bulb, right? As you get more of these things, the probability of collision goes up. So how do we mitigate that and handle it? And one way is just completely over-provision it. So it's a little bit of a shotgun approach. We do a lot of engineering to make these networks work well. And what happens? You can have a well-done network, or you can have a poorly done network. So has anybody ever been on a bad Wi-Fi? No, maybe it was the Wi-Fi's fault. Maybe it was the backhauls fault. Right? There's a lot of different reasons. Whenever you have a bad experience, everyone says the Wi-Fi's broke, but it could be anything in that path. But this is why. There was a lot of latitude in what kind of a network that you would deploy. Now, as we went into Wi-Fi 6, everything changed, because what we did is we enabled an OFDMA stack, which means that we could schedule in the frequency domain as well as in the time domain. Now remember, if there's a lot of different devices vying for the network, they're waiting for people to transmit, and then when they hear the air go clear, listen before talk, then they start to transmit. Now what we got with OFDMA, with frequency division, is now multiple things can be talking in that frequency at the same time. Now if you're muxing on the frequency domain, the number of times you mux, for every one of those, you eliminated a potential collision. And so if you've eliminated collision, then you've eliminated that back off, and if you've eliminated that back off, then you've eliminated some of that non-deterministic type capability. So we added frequency division. The other thing that we added in Wi-Fi 6 is this ability to schedule from the network. So instead of just everything trying to vie for the network equally, and just listening to the air and then starting to transmit, in Wi-Fi 6, what we could do is we could say, you talk, now you talk. Now you talk, and we could coordinate that. Not only could we coordinate it, but we could take, remember I said that upper stack policy, and we could coordinate those communications based on the applications and services that were most mission critical to you. So with Wi-Fi 6, two big things, that frequency division and the ability to schedule from the network. We added puncturing, and I'll talk about puncturing in a minute. Now, the other thing that happened is Wi-Fi 6E. Remember I said we have the stack, and it has to be a capable stack, and we have to be able to address this interference that sometimes we can't control in an unlicensed environment that gives us that response. You know, what kind of performance we get, I don't know. That's what we're trying to eliminate. So Wi-Fi 6E, I hate to call it a shotgun approach, but one way to solve the interference problem is to throw a lot of spectrum at it. Right? Now, every time we throw spectrum at Wi-Fi, it gobbles it up. So it's going to happen again. In fact, I think in 6 gigahertz, it's going to happen faster, because we don't see just the .11 stack there. We see 15.4 stacks. So you see things like Matter, like Thread. You see, traditional Zigbee type protocols. And what's happening is that these APs are becoming multi-radio platforms. Bluetooth is going into 6 gigahertz. VLP is in 6 gigahertz. So you have all these things that are vying for those resources. When you have all those things vying for resources, what happens? They start colliding again, right? And so adding more spectrum buys us some time, but it doesn't ultimately solve the problem in the end. So enter Wi-Fi 7. Now I've read all sorts of articles on Wi-Fi 7 and what we're doing in 7. I call it 7 plus. Some of these things are specifically in 7. Some of them we're developing for 8. Some of them are actually across 7 and other protocols like QoS. But a lot happened in Wi-Fi 7, and you read these articles saying, well, Wi-Fi 7 doesn't really get you anything. you know, you can do this with the previous protocol stack. I'm going to show you some reasons why it really makes a difference, and I'm going to show you how applying these technologies can make a difference in determinism. All right, now I broke the fundamental rule of keynotes on this slide. This slide's too busy. I know that, but stick with me for a second, because what I want to show you here is an example of how the development in the industry is addressing both the stack capability and the ability to manage for interference. Both of these are happening simultaneously. So we are moving into the domain of more predictable wireless. So WMM has been around for a long time, and we actually get some pretty good improvements. This is pretty universal. Everybody's using it. I'm going to show you what it gets us. If you look at TUA, or Triggered Uplink Access, what that does is it allows the device to say, I have this traffic to send, and if you have an extension on that, you can say, I have this traffic to send at this frequency. Since the network is doing the schedule, please schedule me at this frequency. So now there's this communication that's happening between the device and the network to coordinate their service. So again, this is something that we didn't have before. And remember, the uplink is really the hard one. In the downlink, we have this QoS management. I show low adoption here because this is some of the new features that are happening in QoS Release 2 over at the WFA. But there's been mechanisms in networks for a long time to handle the downlink. At Cisco, when we see the flows come down, we can choose when we get to the AP how to schedule that based on the policy of the network. But you know what was really hard to do? Was to get control on the uplink. When does the device talk, and how do you manage that? Because they just start talking on the network. So when we see technologies like TUA, what we're doing is we're addressing that uplink. Well, then we have MLO, multi-link operation. I'll show you a little bit about that in just a second. But multi-link operation does two things. Not only does it lower latency, so it's a stack improvement, but it's using multiple pieces of frequency. And why is that important? Because when we have interference in one piece of frequency, we can assure the packets get through on the other frequency, and then MLO can move these channels around based on where it's getting the best throughput in real time. So it's managing both the frequency domain and the ability to get a more resilient latency characteristic. RTWT, I'll show you a little bit about that. Puncturing is all about protecting interference. As we go into 6 gigahertz, we have a lot more spectrum. So what happens is that the wider your channel, say you're using an 80 or 160 megahertz channel, right, and you get a little 20 megahertz piece of interference, then that channel gets busted up. You have a problem. It has to stop transmitting. So you don't really want to stop a 160 megahertz channel because you're getting this little bit of interference. So what you can do is you can recognize the interference and then schedule on both sides. So you see what's happening here? What the industry is doing is they're solving both the stack scheduler problem by policy, and they're solving this problem of unlicensed in the interference domain. And if we can put these two things together, we get something that's far more predictable. So again, I know, busy slide, but I think this is the little bit under the covers of what's actually happening and in what release it's being certified and whether it's mandatory or optional by the WFA when you do that certification. So just to show you a couple of other technologies that are happening, I don't know how many people have heard of L4S. And people heard of L4S, you're starting to see it. I think Apple, Dean has seen it. So Apple has been chairing this group, and it's interesting because now what we're doing is we're not only looking at the air interface, because it's the air interface that often congests, because you can almost think of an air interface as sort of a mux instead of a switch, but it's also congestion that you can have anywhere else in the network, including the WAN. The typical places that we get latency is either on the air interface or in the WAN. And what L4S does this actually have a pointer? Ah, it does. So what L4S does is, as you're going hop by hop across here, what it will do is if there's congestion at any point, say this is your SD-WAN router, and there's congestion going into the WAN, what it'll do is it'll mark a congestion indicator that when it gets all the way to the end, it gets to the server, that gets reflected back to the sender. Now, if you do that, now the sender knows, hey, there's congestion in my path. And for a lot of these next generation applications where you need low latency, it's often having to do with codecs that are doing things like WebEx. So it's a video codec or it's a voice codec, right? Or you're doing something like augmented reality or virtual reality. Those are all codecs. And if you see congestion, you can actually codec down. So you can degrade a little bit in quality in order to get a much more reliable latency experience. Now, if you have a lot if congestion is happening here, you're getting a lot of congestion indications back to the clients, which means now that all the clients together only have to slow down a little bit for everybody to solve everyone else's problem. So again, we look at this on the air interface, we're looking at this end to end, but this is how you get this deterministic behavior. Remember I said when the Wi-Fi doesn't work, people say the Wi-Fi is broke? Well, it might have been that SD-WAN connection and have nothing to do with the Wi-Fi, and these are ways that you can actually get that quality of experience all the way through. MLO I'll talk about in a minute, and I already talked a little bit about TUA and what we can do in the uplink and also restricted TWT. Now I don't know, and I'm going to be completely honest, I tend to be very open when it comes to technology. I don't know if restricted TWT will get adoption or not, and I'll show you why in a minute in the charts. But what it basically allows to have happen is that if you have a mission, if you have something that's very delay sensitive, like this headset, and you have all this other traffic that's happening, the headset can tell the AP, hey, I need to be serviced at a certain rate, and then the AP can actually reserve slots both in the time and frequency domain. And then nothing else, and what it'll do, that AP will tell everything else on the network, don't transmit during this slot. So it's reserving a little piece, you know, a little bit of opportunity to transmit. So you can see it's transmitting, transmitting, transmitting. Now this guy wants to transmit. He knows for that transmit opportunity, don't be bigger than this space because this mission critical communication needs to be able to get through. So these are the types of stack improvements. So what I'll say is, are we getting something for Wi-Fi 7? I would say yes, we are. How much of it gets implemented and how fast it's adopted, I think we can debate, but the technology is there. I'm going to be real quick because I'm really running out of time. So this is MLD or MLO, multi-link device or multi-link operation. There's a lot of different modes for this. The two that are the most important are this EMLSR, so this enhanced multi-link single radio where you can use both pieces of spectrum to receive and transmit, which means that you can go to a good channel if you're having interference on another channel. And this other one, this simultaneous transmit and receive, which means that you're getting more throughput at the same time that you're getting the resiliency. So MLO, if people say Wi-Fi 7, MLO is almost always the next thing that they talk about because this really makes a big difference. This is just an example of puncturing. What you see here is without puncturing, no interference, everything gets through the channel fine. Here in legacy networks, if you got interference, then what happened is you lost all this bandwidth and the radio resource management would move to a smaller channel to avoid it, and you just wouldn't get this capacity. With puncturing, what you do is you say, I can't use this piece, so now I'll transmit on both sides. So these are big efficiencies to what we had before and how we can do things like mitigate interference. So I'm almost done. So this is the difference. So this is some of the testing that we've done and some of the data that we've pulled together. And what you can see here that if we have a 50% channel utilization on a 40 megahertz channel, if we're doing no quality of service, this is actually pretty good. And this is how we built networks in the past. If you're under 50% utilization, no quality of service at all could get you, even in dense implementations around 20 milliseconds. That's not bad. That's really not bad, right? And then if you add WMM, we're down below 15, worst case, 99.9 percentile. If you do MLO, now you're getting resiliency and a little bit of an improvement. TUA brings it down further, and if you do RTWT, you're down to a couple milliseconds. Okay, so these are pretty significant in their changes. Now, what happens when you hit 90% channel utilization? And I know a lot of you design networks, and you're going to tell me, well, you don't never run at 90% utilization. Are you crazy? That breaks Wi-Fi. And you know what? It would in Wi-Fi 5, right? But as we go into these next generation, it doesn't. Now, why am I showing 90% utilization? Because data traffic tends to be very bursty, and the way that devices go onto the network tend to be bursty. And what that means is that you get these perfect storms of transmission. So even though your overall channel utilization can be managed to be fairly low, you're going to get these bursts of high channel utilization. And when you get the burst, the legacy technologies break down. And that's where you get the retransmits, and that's where you start to get these really high latencies. So you can see here, 250 milliseconds latency during these bursts. And what does that do? That breaks some of your next generation real-time applications, right? Now you start to apply things. Look at the gain just in WMM. But the scale's a little bit different now. This is still 50 milliseconds. Well, 50 milliseconds doesn't solve what we want for WebEx, for video teleconferencing, and for some of these next generation applications for manufacturing. They want lower latency than this. MLO gets you resiliency and a little bit of an improvement. Look at TUA is right down there where we need to be for most services and applications. And then if we go all the way to RTWT, look at this, same traffic, 90% channel utilization, and for your mission critical traffic, down there at 1 millisecond. You couldn't do that in Wi-Fi 5. So does Wi-Fi 7 add new functionality and capability that can take us into the next generation of application and services? I would say most certainly yes. All right, so this is what's coming. Like I say, the technology's in there. We'll see how long it takes for things to start to adopt it. Some of these things require collaboration with the end device, but as we start to certify more and more of this, we end up in the right place. So with that, I'll wrap up.
Thank you. Time for one question to Matt. Anyone?
Too early.
Too early. Everyone is familiar with Wi-Fi 7 and all the new capabilities.
All right.
Okay, Matt, thank you. Good to see you. Thank you for coming.